In the realm of machine learning, data streams pose unique challenges, particularly in terms of data normalization. This research paper delves into the effects of normalization policies and distance functions on classification accuracy within data streams. The authors argue that experimental protocols assuming a fully normalized stream can lead to unrealistic and biased results. They evaluate 8 well-known distance functions: Euclidean, Manhattan, Chebyshev, Minkowski, cosine, Mahalanobis, standardized Euclidean, and Canberra under different stream scenarios. Their findings indicate that utilizing the original data stream without normalization, combined with the Canberra distance function, can provide more realistic and better results. Moreover, distances such as cosine and standardized Euclidean are found to be more sensitive to feature changes over time compared to Manhattan and Canberra distances. The paper emphasizes the importance of considering the normalization policy and distance function when dealing with data streams. It highlights that unrealistic assumptions about the stream, such as knowing the minimum and maximum values of each feature in advance, can lead to poor results. The authors employ the min-max normalization strategy, which is simple to compute and understand but sensitive to outliers due to its reliance on minimum and maximum values. The paper also discusses related work on data streams, emphasizing the importance of considering the serial dependence of the data and the need for adaptive normalization techniques. It highlights the limitations of current approaches and the necessity for more realistic experimental protocols. The research further explores the impact of different normalization policies and distance functions on the performance of a KNN classifier in data streams. Using a synthetic dataset, C-concepts, the authors test the performance under different scenarios, including varying feature ranges and normalization policies. The results suggest that the choice of normalization technique significantly influences the classifier's accuracy, with the Canberra distance showing promising results in some scenarios. The study also underscores the importance of considering the previous batch for normalization, as it often leads to better performance. Additionally, the paper includes experiments using real-world datasets, such as airlines and gas sensor, to further validate the findings. Ultimately, the research emphasizes the need for careful consideration of normalization policies and distance functions in data stream applications to achieve optimal performance. This research paper delves into the impact of different distance metrics and normalization approaches on classifier accuracy in various datasets. It presents a comprehensive analysis of 8 distance functions: Euclidean, Manhattan, Chebyshev, Mahalanobis, standardized Euclidean, Minkowski, Canberra, and cosine similarity, and 3 normalization methods: no normalization, full dataset normalization, and normalization with the previous batch. The study demonstrates that the Canberra distance is the most resilient, leading to good results in various scenarios. The authors emphasize the importance of avoiding full dataset normalization, as it can lead to biased results. Instead, using the original data or normalizing with the previous batch can be beneficial. The study concludes by recommending the Canberra distance as a default metric for stream scenarios due to its simplicity and effectiveness. The paper also investigates the impact of 8 distance functions and 3 normalization approaches on data streams, using 1 synthetic and 5 real-world datasets. The results show that the normalization policy significantly influences the classifier's competence in data streams, with the original data without normalization yielding the best results in 3 out of 5 tests. Different distance functions lead to varying results, with the Canberra distance function showing the best performance in most tests. The study highlights the limitations of this work, including the lack of consideration for scenarios where feature ranges change frequently and the overhead of updating normalization over time. Future works aim to test other scaling techniques, such as the z-score, and explore other classifiers and classification techniques that depend on distance metrics. The paper provides a comprehensive review of related works, citing numerous studies on concept drift, data normalization, and distance metrics. It references papers on adaptive normalization, leakage in data mining, and comprehensive surveys on distance similarity measures between probability density functions. The study's findings have significant implications for real-world applications, such as concept drift adaptation techniques in distributed environments for real-world data streams. The author's suggestions for using the original data without normalization and the Canberra distance function can be applied to various domains, including electricity, gas sensor, and cover type datasets.